Hello everybody, this video is going to be about something called partial pressure calculations. We're going to learn that if you have a mixture of gases in a container, that they're each going to contribute to the overall pressure, which makes sense because they're each hitting the sides of the container, they're each exerting pressure. So we're going to learn how to do calculations where we can figure out what the total pressure is, or how much pressure is coming from one particular gas, or maybe what would happen to the pressure when I mix these gases together, things like that. So first is the very basic principle that all of this is going to be based on, which is called Dalton's law. Dalton's law is the one that says that the total pressure is going to equal the sum of all the individual pressures. So the pressure from gas 1 plus the pressure from gas 2 plus the pressure from gas 3, etc. For however many gases you have. You add them together and you get the total pressure for the entire container. Remember, we're doing these typically in closed containers, so that's why I call it container. Right? They're going to be hitting the edge of those containers. That's what exerts the pressure. One of the big assumptions here is that the gases are not interacting with each other. If they interacted with each other, then things would get a little bit more complicated. We'd have correction values, just like when we were talking about the ideal gas law. So, as always, we pretend that these are ideal gases. And if we pretend that they're ideal, then the total pressure is simply the sum of all of those what we call partial pressures. The little baby individual ones we call partial pressures. So let's look at partial pressure a little bit. I have a canister of gas. These molecules are bouncing around and they are exerting 200 kilopascals of pressure. I have another gas. This one is exerting 500 kilopascals of pressure, a little bit more pressurized. This container is under 400 kilopascals. If I'm going to combine them all into one container, I'm not changing the temperature, I'm not changing the size, all I'm doing is I'm putting them into the same size container. I'm combining them. What would my pressure be? Well, Dalton's law tells me that I'm going to add them together. It's as simple as that. 200 plus 500 plus 400. We have 1,100 kilopascals of total pressure because each of these partial pressures is still contributing to the overall total. I will tell you, we see a lot of addition mistakes here. When we do Dalton's problems, people will do the whole giant calculation and then they'll add wrong. So I have no shame in using a calculator. I don't do math in my head. I use a calculator, right? So please be careful with your addition. I think sometimes we get so focused on all the crazy algebra we're doing that we make small mistakes like adding and subtracting. So just be a little bit careful, use a calculator if you want to. One classic example of looking at these partial pressures is the air pressure that we feel. So if we have a little person here on Earth, they are having all different types of gases pushing down on them. Remember that air is a mixture. So we have some oxygen, we have nitrogen, argon, carbon dioxide. There's more than that, but we're just going to use those for our example today. Okay? Well, nitrogen is exerting 590 millimeters of mercury worth of pressure on this poor little person. Most of the air is the nitrogen here, right? So a huge portion of it of the pressure is coming from the nitrogen. At the same time, the oxygen is pushing on them, the carbon dioxide, the argon, it's all contributing. All those collisions are happening. So if I want to know the entire pressure that this little person is experiencing, I'm going to use Dalton's law and I'm going to add them together. So let's do that. Go ahead, add up those numbers. We have 149 plus 590 plus 3 plus 8. Altogether, this person is experiencing 750 millimeters of mercury worth of pressure on them, which is almost what we call 1 atmosphere, right? So this person's a little bit above sea level. They don't have quite as much pushing down on them, so they're a little bit higher probably. Okay. One thing that's weird that really bothers people is that the type of gas doesn't matter. People hate that. It's one of the things that people are always grumbling about when we're in the gas chapter is, well, it should matter, they're different, but you got to remember we're pretending these are ideal. And if they're ideal, they take up no volume of the atoms themselves. And if the atoms themselves don't take up any volume, then there's nothing to distinguish it, right, from another gas. And so it doesn't really matter what it is. We're going to get the same answer. So if you look at these 3 examples here, in the first container, I have 1.75 moles of helium. I have certain temperature and volume conditions, right? Think about our ideal gas law, right? PV equals nRT. We can calculate the pressure. Well, over here, in this container, I have 0.75 moles of hydrogen, 0.75 moles of helium, 0.25 moles of neon. I have 3 different things, but the total number of moles is the same, isn't it? Which means if we're at the same pressure or same volume and same temperature, we'll have the same pressure being exerted. And over here, we have a mole of nitrogen, half a mole of oxygen, 0.25 moles of argon, all different gases, different quantities, but the overall total number of particles is the same. The temperature and the volume is the same. So it won't matter what these gases are. It doesn't matter, what ratios they're in. If you end up with the same number of moles at the end, you're going to have the same total pressure. Now your partial pressures will be different, right? In each case, each gas is exerting a different partial pressure, but the sum of all the pressures will be the same. We use sometimes what we call mole fractions to help us find partial pressures. When we have a gas mixture, the partial pressure is going to be what that one gas would exert if it was all by itself in that container. And since this is all coming down to how many particles are colliding, right, the number of moles, you can calculate the mole fraction to see how much of that mixture is a certain gas, what fraction of the gas. Is it half? Is it 1/3? Is it 7/8? What fraction of the particles are coming from each gas? So some examples, right? You would write X, we use X to represent mole fraction, and you use a little subscript to say of gas 1. The mole fraction of gas 1 is the number of moles you have of that gas over the total number of moles in the container. If you had a second gas, it would be the same thing. The mole fraction is the number of moles of that gas over the total. So if I want to know the partial pressure for gas 1 and the partial pressure for gas 2, what I can do is use these fractions to see what fraction of the total pressure is coming from each gas. So the partial pressure of gas 1 is the mole fraction of gas 1 times the overall total pressure the container is feeling. For your second gas, the partial pressure of gas 2 is the mole fraction times the total pressure. Now, if you think about mole fractions, if you were to add those together, you should get 1, right? Just like if you have percentages, 80% and 20% should equal 100%. If we're doing fractions, right? If we have 1/4 plus 3/4, it will equal 1. So you can think of it, you can sometimes solve for one of your mole fractions by subtracting from one if you know the other mole fraction. So there's little manipulations that you can do, and those will come with seeing practice problems and trying them. If you then calculate your partial pressures, right, they should add back together to give you your total pressure. You can do this with, 2 gases, 3 gases, 4 gases, as many as you need to. So let's try a problem. The total pressure of a mixture is 97.4 kilopascals. Find the partial pressure of each gas. So look at my little cartoon picture here. I have 3 moles of helium and 4 moles of neon all in the same container. And what I want to know is what would the pressure be if I only had the white circles? What would the pressure be if I only had the black circles? Those are the partial pressures. 97.4 is the pressure of all of them together. What would they be by themselves? So let's do helium first, and then we'll do neon. Well, we need our mole fraction. There's 3 moles of helium, and all together in the container are 7 moles of gas, right? So my mole fraction looks like that. 3/7 of the gas is helium times my pressure, and I find out that of the 97.4 kilopascals, 41.7 of them are coming just from the helium. Let's do the partial pressure of neon. This time there's 4 moles of neon over 7 moles of gas times my total pressure. So 4/7 of the gas is coming from neon. And I get my final answer. At this point, everybody starts going, wait, can't you just subtract? Couldn't you do 97.4 minus 41.7? Yes, okay, but I always caution people against getting an answer to part 2 that relied on you doing part 1 correctly. If you hit your calculator wrong for the helium calculation, and then you're going to base your neon answer off of that, you're going to get both wrong. If you do each problem individually, you have a higher chance of being safe from any small errors from previous parts of the problem. It's not that I wouldn't give you credit if you had subtracted and it was correct, but if you subtract and it's wrong because part 1 is wrong, well, now you get no points. So just a suggestion, mathematically you're correct. You can subtract, no big deal. I just always want to tell you what's safest, okay? Now, it'd be nice if it stayed this simple, wouldn't it? But it doesn't, okay? This is a classic of time when we start layering on other topics. This comes up in AP Chem all the time because they try to tie together all sorts of different manipulations of numbers and throw in some dimensional analysis and maybe throw in some stoichiometry, and it just starts getting really crazy. Sometimes the problems are super short, sometimes they take 2 pages, okay? It's not that they're complicated steps, it's that there can be lots of steps, which gets tricky. So let's do a problem where we add in some molar conversions. This time, I didn't tell you how many moles, did I? This time, what did I give you? I gave you grams. Grams are useless. We gotta get to moles. We always get to moles. So, we have 3 gases. We're going to do 3 molar conversions. Then we're going to do 3 mole fractions and 3 partial pressure calculations. And that's 1 question, okay? So let's start. I have 80 grams of helium. 1 mole of helium weighs 4 grams. I find out I got 20 moles of helium in this container. I have 80 grams of neon. 1 mole of neon weighs 20 grams. I have 4 moles of neon. 80 grams of argon. 1 mole of argon weighs 40 grams. This container has 2 moles of argon. Since I have to do mole fractions, I need the total moles, don't I? That's my denominator. So if I add these all together, I find out I have 26 moles of gas. Now I can do 3 different mole fractions. Helium is 20 over 26. Neon is 4 over 26. And argon is 2 over 26. Please do not reduce these. Remember when we learned about the mole ratio and I told you don't reduce it, let your calculator take care of it for you? I'd like you to do the same thing here. I would like you to leave them alone, let your calculator do it. Because if we leave them like this when they're not reduced, it's really representing more accurately what's happening. We have 26 moles of gas and 20 of them are helium. Okay, so I'd like you to just leave them, don't reduce them. To get my partial pressures, I'm going to do mole fraction times the total pressure, and the total pressure was 780 this time. So this times 780 gives me one answer, this times 780 gives me one answer, and this times 780 gives me an answer. I'm going to have 3 separate answers. So 20/26ths of 780 is 600. 4/26ths of 780, 120. And 2/26ths of 780 is 60. I find out most of the pressure is coming from the helium. I had the same number of grams, but the pressure that's being contributed is completely different, isn't it? Because the moles are different, which means there's way more particles of helium hitting the container than there are of neon or argon. Okay. All right, the next manipulation that we're going to do is we're going to take partial pressure calculations and we're going to smush them together with Boyle's law calculations. I'm not going to lie, I kind of hate these problems. You guys, there's so many numbers, there's so many containers, things are changing, there's, container 1 at the beginning and container 2 and then the container 3 and pressures and volumes and mole fractions, and it's so much. You have to be organized. I swear 95% of teaching chemistry is trying to get you to be organized, right? And this is a perfect example of why it matters. So keep track of the charts, fill things in, try to focus on visualizing where the gases are going. I think that's really helpful in these problems. Okay? All right. We have 2 1-liter containers. We have container A and B. It's very helpful to label them. Okay? They contain gases. Container A is 2 atmospheres of pressure, and container B has 4 atmospheres of pressure. Both gases are forced to mix into a brand new container, container C. This container has a volume of 2 liters. We want to know what the total pressure is by the time we're done. We cannot just add those together. It is not 6. You don't do 2 plus 4. It's not that simple because the volume size changes, right? And so it's not a direct addition that we can do because one of our variables is not being held constant, okay? I think it's incredibly helpful to sketch pictures of the containers and to label them. It's incredibly helpful to use subscripts and be consistent, okay? So, sketch container A and container B. Look, container C is bigger, isn't it? We're going to take container A and B, and we're going to add them to container C. Now here's our crazy chart, okay? We have pressure for each container and a volume for each container. We have the before values and we have the after values, right? P1, P2, V1, V2. The problem is that we have P1A and P1B, V1A, V1B. By the time we're done, we just have one volume, right? But we have two partial pressures, don't we? Okay. If we add up our partial pressures, we'll get our total pressure down here at the end. So let's start filling in things. Let's start doing some calculations. We know that container 1 begins the problem, the starting value is 2 atmospheres and 1 liter. Container B is 4 atmospheres and 1 liter. Container C, at the end of the problem, when we've combined everything together, is 2 liters. But we need to find out what the partial pressure is of A, because it's not going to be 2 anymore. It's changing container size, the pressure will change. Remember, Boyle's law is what happens when we have pressure and volume and we're trying to find what that change would be. So the pressure, if container 1A, the pressure of container A at the beginning, the volume of container A at the beginning equals the pressure of the new container from gas A and the volume of the new container, right? Oh, too many subscripts, okay? Compare it to your chart. We have P1 V1 equals P2 V2, okay? The partial pressure from container A, gas A, in the new setup in the bigger volume container is 1. And that makes sense, right? If you increase your volume, your pressure should go down. So let's do it again for gas B. We started with 4 and a liter of 1. When we're done, we don't know what it is, and we know that it's 2 liters. There we go. It won't always just cut in half, right? You're not necessarily always going to have a nice simple, doubling of your container. So now we have 2 partial pressures. If I want the total pressure, I just add them together. I end up with 3 by the time I'm done. Okay? So you can see what I mean with there's just a lot of numbers here. There's a lot of containers, there's a lot of things changing, but in the end, you already know how to do Boyle's law. You can do a Dalton's partial pressure calculation. Each piece is not complicated. Putting them together, it gets a little bit worse. All right, let's do another one. This one's horrible because there's so many more containers. Okay, we have containers A, B, and C, and we're going to smush all those gases into container D. They're all going to get added into container D. Okay, we have a volume and pressure for each. We have a volume of our ending container. We don't know what all our pressures are going to be. So let's fill out our chart. Container A, 3.2 atmospheres, 1.3 liters. Gas B, 1.4 atmospheres, 2.6 liters. Container C, we get all that filled in. We know that our ending container is 2.3. They're all going to end up in the same place. Okay? Now, this could be even worse. What if I gave you milliliters for one container and I gave you torr for one of your pressures, right? I mean, it can start getting lots of little bits added in here. We have 3 gases. We need 3 partial pressures. We have to do 3 Boyle's law calculations. 3, okay? So let's do A first. P1, V1, P2, V2. We're starting with container A, and we're ending in container D, but we're worrying about the gas A, right? So you can see that if you look, our volume went up, our pressure went down, which makes sense. Bigger container, the particles won't hit as often, the pressure will be lower. Next Boyle's law calculation for gas B, 1.4 times 2.6 is whatever our pressure is times our new volume. This makes sense. Our volume went down, so our pressure goes up. One more Boyle's calculation, this time for gas C. Let's try to predict what will happen. I start at 3.8 liters and I'm going down to 2.3, so my pressure should end up higher. It's a good thing to try to check, right? Always ask yourself, should it be higher or lower? We plug in our numbers and we find out, yep, pressure went up. So now if I want my total pressure, I just add all of these partial pressures together, don't I? So you can see how the concept of just add up these 3 numbers is easy, but it's all the layers of how do you get those 3 numbers that gets a little bit tricky. Okay? The good thing is, not very many problems are this crazy. Okay, so that's really nice. All right, next is a concept that uses Dalton's partial pressures and is incredibly important to lab stuff, okay? Very, very important. When we are doing some kind of experiment that's making a gas and we collect that gas, one of the ways we do that is by collecting over water or collecting via displacement, okay? So the gas is being created. We have an upside down container here in a bucket of water, and there's a tube that will allow the gas from the reaction to go into this beaker, into this flask. And it's going to come up to the top, and what's going to end up happening is it's going to push the water that was in there out, and it's going to take its place. It's going to be displaced, okay? So the gas is created. It's going to push the water out of the flask and displace it. That's going to allow you to find the volume of the gas. If this was just open, you can't collect it, can you? So this is a very easy, simple way to collect some gas and to get the volume. One of the things that we do is we make sure that when we're finished, that we lower or raise the flask until the water level in the container and in the flask are equal. If you get those water levels equal, then what ends up happening is the pressure inside the container will be equal to the pressure outside in the room from the atmosphere. I cannot easily measure the pressure inside this flask, but I can measure the atmospheric pressure in the room with a barometer very easily, right? So I don't have a little device to stick in here to measure the pressure. So I'm going to end up measuring it indirectly by using the atmospheric pressure. There is a bit of a problem though, is that the water gives off vapor, right? And so when you are collecting your gas up here, it's not pure gas. It's gas and a little bit of water vapor. We call this wet gas. The gas is not pure. It's mixed with the water vapor, which is why we call it wet, okay? So the collected gas is going to have this water vapor mixed into it. And that's going to mess up our calculations, right? Because now it's not 100% of the pressure coming from our gas. Some of the pressure will come from the water vapor. The amount of water vapor will change based on what temperature you're at. If you're at a low temperature, you won't have as much water vapor. If you're at a really high temperature, you're going to have a lot more water vapor to deal with. The question is, how do you know how much water vapor? And that's going to be from just looking at a chart, okay? So to find the pressure coming from the water, you have a chart and you find the temperature. I literally sat there with a calculator. You can find these calculators online where you type in a temperature and out pops the water vapor. And I literally made a chart for every degree, okay? So that should be very helpful to you, okay? You can, there's a link on there if you need to use the actual calculator to get one if you have like 27.4 degrees, right? But if it's a nice, round number, you'll be able to use this chart. So the total pressure inside your flask or whatever container you're using will be a result of the wet gas, right? And so what you need to do is subtract out the water, and that will let you get the dry gas, is what we call it. So total pressure is the dry gas that we're interested in, plus all that water vapor that we don't want. So if I want just this partial pressure, I'm just going to subtract that from the total pressure, the atmospheric pressure. Once I have this dry gas partial pressure, that's going to allow me to use the ideal gas law and calculate how many moles of gas were made. Then I can sometimes use that information to figure out what the molar mass of the gas was. I could even figure out what an unknown gas is by using this idea of water displacement. It's a pretty simple technique that gets you a lot of useful information. AP Chem problems love this idea. You're always having to subtract out water vapor from those problems. Let's do an example. Hydrogen gas is collected over water at 22 degrees. Find the pressure of the dry gas if the atmospheric pressure is 708. So remember, the pressure in the bottle is equal to the atmospheric pressure, right? Because we've equalized those by moving the container up and down so the water levels match. We know the total pressure, but we don't know the partial pressure of that. But I can find the partial pressure of water by looking it up on the chart. One of the things that's hard for for people on these problems is that it's not going to tell you to go look up your water vapor. People act like they're not allowed to do that. They feel like they're doing something wrong by looking elsewhere for information. But you have to. That's the whole point. You have to reference the chart, okay? So when I look at the chart and I look at 22 degrees, I'm going to find out that the water vapor will be 19.8. So now all I have to do is subtract, right? I'm going to find out that even though the whole overall pressure in the container was 708, only 688.2 millimeters of mercury were coming from the hydrogen. So that's going to allow me to find my pressure of the dry gas. All right, one more. One thing you should notice is at first glance this seems the same, doesn't it? We don't know our gas, but we know the total. We have to find the water vapor, but uh-oh, there's a conversion, right? Our chart is in millimeters of mercury, but I give you atmospheres. It doesn't matter if you convert atmospheres to millimeters or millimeters to atmospheres. It doesn't matter. The rounding will be a little different, but it won't matter, okay? As long as you make sure your units match, you're fine. Then we're right back to the same. We know that Dalton's law of partial pressure tells us that we have to add these values together to get the total. If I know the total and I know the water, I'm just going to subtract and I'll get the pressure of my dry gas. Okay? All right, everybody. That was a very long lesson on how to add numbers, right? That's what Dalton's law is, just adding numbers. You can see what I mean by we are taking a very simple addition concept, add up your values, and layering on the things that we've done earlier with Boyle's law and molar conversions and unit conversions and things like that. Okay? I promise that the more of these you practice, the more robotic it will get. Okay? The first couple are going to feel a little overwhelming. I'm not going to start you off with one of those horrible Boyle's Law ones, I promise, okay? Just remember that just like in sports, right, people practice for their sports over and over and over. People practice for piano over and over and over, right? You got to practice your skills in a repetitious way, right? You got to repeat them over and over, and this is no different, okay? So just go slow, use pencil, right? Get a couple done, and you'll start to see that it does get a little bit easier. All right, everybody, that was it for this lesson. I hope that was helpful. Bye.